Hello everyone, tonight is the second night of related rates. So tonight we're going to tackle problems that deal with rates with the areas or circumference of circles, the surface area or volume of spheres, and also the volume of a cylinder. So one of the big things that you're going to have to do is make sure that you know all of your formulas and memorize them. You might want to make some flashcards for the different formulas because they are not given to you on the exam, and so I will not be providing them for you as we move through. Okay, taking a look at this first problem, it says, suppose oil spills from a ruptured tanker and spreads in a circular pattern. If the radius of the oil spill increases at a constant rate of 1.5 meters per second, how fast is the area of the spill increasing when the diameter is 60 meters? Okay, the first thing we want to do is read through and make sure that we understand what shape we are dealing with. So here it says that the oil is spilling and spreading in a circular pattern. So clearly we're talking about a circle here. All right. And so read through it again and talk about and find out, what are we talking about that circle? Are we talking about the circumference? Are we talking about the area? What formula do I need? So it says if the radius of the oil spill increases at a constant rate of 1.5 meters per second. So radius is increasing at a rate. So that sounds like dr dt. Okay, and that's 1.5 meters per second. How fast is the area of the spill increasing? So it looks like we need dA dt, and that's what we don't know. So we're definitely talking about the area when the diameter is 60 meters. So the diameter of my circle all the way across is 60. Okay, so what we want to do first of all is go ahead and pull out of our brains the formula for area of a circle. And so hopefully we all know this one. Area of a circle is pi r squared. All right, and so we're talking about finding out how fast the area of the spill is increasing. Well, that sounds like I need to take the derivative with respect to time of this formula. And so when I do that, I get dA dt equals, now remember pi is a number, so when you take the derivative of pi r squared, it's just 2 pi r and then dr dt. All right, so if I look here at all the pieces that I need, dA dt is what I'm looking for. 2 pi are just numbers. R is radius. Well, they gave me obviously the diameter up here. So if they give me the diameter is 60, I know that my radius is 30. So we want to make sure that we're not fooled by that, that we know to properly convert that. And then dr dt they give me. So at this point, I'm ready to just go ahead and plug in. So dA dt is equal to 2 pi times 30 times 1.5. Okay, so if I kind of take this over here, I know 1.5 is the same as 3 halves, so I'm just going to erase it and write it like that so that I can see that 2 times 3 halves, the 2's go away, and so 3 times 30 is 90 pi. So dA dt is 90 pi, and then of course I need my label. So if we're talking about the radius was increasing at a rate of 1.5 meters per second, I know that my area is going to be meters squared per second. All right, and then we want to get in that habit of writing that concluding sentence. So we would go ahead and say that the area is increasing at a rate of 90 pi, oops, an extra line there, meters squared per second. And that is my answer. All right, moving on to the next one. All right, the second question reads, a ripple on a pond's surface expands such that its circumference increases at a rate of 25 feet per second. How fast is the area of the ripple increasing when the circumference is 49 pi feet? Okay, so it sounds to me like we're dealing with two different things here. Both of them, though, circumference and area, lead me to believe, and just think about what a ripple in a pond surface looks like. It's a circle that just keeps growing and rippling out further and further. So that's what we have, all right? So really, I just want the one circle drawn. So I have my circle, all right? And now it says, go back and try and unpack what information are they giving us and write that all down. So it is expanding such that its circumference increases at a rate of 25 feet per second. So dc dt is 25 feet per second. How fast is the area of the ripple increasing? So again, I'm looking for dA dt. That's unknown. When the circumference, so they do give me circumference, is 49 pi. All right, so clearly I know a lot of information about circumference, and I need to find my dA dt. So if I look at the formula for, obviously dA dt is rooted from the formula for area. So if I look at my formula for area, I know it's pi r squared for a circle. And so if I take the derivative of that, dA dt is equal to 2 pi r dr dt. So this helps me know exactly what I need in order to find dA dt. What is it that I am going to need to plug in? Well, I'm going to need to plug in my radius, and I'm going to need to plug in my dr dt, neither of which I was given. All right? So I'm going to have to work backwards from the formulas that I'm given in order to plug in the necessary information. All right, so one of the formulas that I was given was for circumference, and one was dc dt. So let's start with the circumference formula and see if we can remember it. So the formula for circumference of a circle is in fact 2 pi r. All right, some people remember it as pi d, but since it's radius that we want, I'm going to always remember it as 2 pi r. All right, so now if I fill in the circumference as 49 pi equals 2 pi r. And so now I should be able to solve for the radius based upon that circumference. So in fact, I know that the pi's are both going to cancel out, so I get 49 halves is equal to my radius. Okay, so now I have my radius, and I can fill that in on here. 49 halves equals r. All right, so I have one of the two missing pieces done. Second thing I need is my dr dt. Well, dr dt is going to come, I want to use my second given information, which was the rate of the circumference. So I'm going to now use this piece. And where does that come from? Well, that comes from taking the derivative with respect to time of the circumference formula. So I take my circumference formula and I go ahead and take the derivative with respect to time. And what do I get? I get dc dt is equal to 2 pi, remember that's a constant, those are both just numbers, so they come down, and then the derivative of r is dr dt. All right, so dc dt I know, that's 25, equals 2 pi dr dt. So very quickly, I can go ahead and solve for dr dt. It's just 25 divided by 2 pi equals dr dt. All right, so now I know all of my missing pieces, so I'm ready to come back over to my area, my dA dt formula here, and plug them in. So dA dt is going to equal 2 pi, the radius was 49 halves, okay, and dr dt is 25 divided by 2 pi. All right, so let's see if we can clean this up a little bit. So dA dt equals, all right, well I can tell that I have a pi, this 2 pi is like over 1. So my pi's are going to cancel here. One of these 2's is going to cancel, doesn't really matter which one. So I have 49 times 25, which I will admit I typed into a calculator, and I get 1,225 divided by 2. So 1,225 halves. And then what is my label on that? Well, we're talking about area. You know, area is a square unit. So since our circumference was given to us in feet per second, then we know our area is going to be feet squared per second. Okay, and so a concluding sentence would be, I'm not going to write it down, but I encourage you to, would be that the area of the ripple is increasing at a rate of 1,225 halves feet squared per second. All right. Okay, so those were two examples that we did on the circles. Okay, we're going to move on from that. So if you're having trouble with those or want to go back and watch one of them again, please feel free. The first one was a little bit more straightforward. This second one brought in circumference and area. So we had to work with what we had and go backwards to find the pieces we needed to fill in to find our the rate at which the area was changing. Okay, the next problem reads, if a snowball melts so that its surface area decreases at a rate of 1 square centimeter per minute, find the rate at which the diameter decreases when the diameter is 10 centimeters. Then find the rate at which the volume of the snowball is changing. Okay, so we have to visualize what is a snowball. Okay, what are they giving us here? Well, hopefully you recognize that a snowball is not just simply a circle, that a snowball is actually going to be a sphere. And so we have the same idea. We have our radius, but we have this, it's my lovely attempt at drawing a sphere. Okay, so we have a spherical ball. All right, and so now go back into the problem, unpack what are they telling us. So it's telling us that it melts so that the surface area decreases. That tells me I'm going to have a negative rate at a rate of 1 centimeter squared per minute. So that's the surface area. Okay, we're going to use capital S for surface area. So its rate would be d capital S dt is equal to negative 1 centimeters squared per minute. Okay, find the rate at which the diameter decreases when the diameter is 10 centimeters. Okay, so hopefully we're recognizing that all the formulas that we have with circle don't use diameter, they use radius. So if they give me the diameter is 10, I know really that the radius is 5. Okay, then find the rate at which the volume of the snowball is changing. So we're going to kind of treat this as like an A and a B. Okay, so our first part is part A, find the rate at which the diameter decreases. Then after we do that, we'll do part B. All right, so in order to answer part A is all talking about surface area. Okay, I know the formula for I know the rate at which the surface area is changing. So what I need now is the formula for surface area of a sphere. Again, this is something that you're going to have to memorize if you don't know it already by heart. So surface area of a sphere is 4 pi r squared. All right, so let's go ahead and take the derivative with respect to time. And so we get ds dt is equal to, remember 4 pi is a constant, okay? So when you take the derivative, you're going to move this 2, your exponent here 2, you're going to multiply it times the whole constant. So 2 times 4 pi is going to give us 8 pi r, obviously decrease your exponent, and then derivative with respect to time, dr dt. All right, so ds dt is what we know. It's negative 1. Okay, we know the radius, so I can fill that in as 8 pi times 5, and dr dt is sort of what I'm looking for. It asked me to find the rate at which the diameter is changing, but obviously the diameter is not part of the surface area formula. But I do know that there's a relationship between radius and diameter. So once I find the rate at which the radius is changing, I should be able to convert that to find the rate at which the diameter is changing. Okay, so this here altogether, going back to the formula here, you get negative 1 equals 40 pi dr dt. Okay, we're going to divide by 40 pi, and so we get negative 1 over 40 pi equals dr dt. Now, like I said, okay, we really wanted the rate at which the diameter was changing. So if the rate at which the radius is changing is negative 1 over 40 pi, well, how do we get from radius to diameter? we double it. So we're going to go ahead and double it, and that's going to give us negative 1 over 20 pi is equal to dd dt. Okay, and of course we need a unit of measure on that. And so our unit of measure here, so negative 1 over 20 pi, and we were talking about the surface area was decreasing at centimeters squared per minute, and so the diameter would be at centimeters per minute, equals dd dt. And again, I would write a concluding sentence that says the diameter is decreasing at a rate of 1 over 20 pi centimeters per minute. And remember, we don't put the double negative, so we already said it was decreasing. We don't need to put a negative on our rate. All right, that was the end of part A, if you will, of this question. Okay, the second part of the question, if we go back, wants us to find the rate at which the volume of the snowball is changing. All right, sounds like we need another formula. We now need the formula for the volume of a sphere. All right, so as we go back here, all right, let's go ahead and pull up our formula for volume. So volume of a sphere, again, one that you have to memorize, is 4/3 pi r cubed. So that's the volume of a sphere. All right, so write that down, star it, make sure you memorize it. So if we go ahead, if we want the rate of change at which the volume is changing, we're going to go ahead and do the derivative with respect to time. So d dt. All right, so that would be dv dt is equal to, all right, here, again, 4/3 pi is our constant. So we're going to multiply that times 3. 3 times 4/3 would just be 4 pi, and then r squared, decrease the exponent, derivative of the radius with respect to time. All right, so that's our dv dt. Now taking a look at all the pieces, what do I need in order to fully evaluate the dv dt? Looks like I need my radius and I need dr dt. Looking back up at the problem, I know both of those pieces. Okay, dv dt is equal to 4 pi. My radius was given to me here as 25. No, I'm sorry, my radius was given to me as 5. I go ahead and square that, and I'm going to have 25. And then dr dt I found to be, remember dr dt, not dd dt. So it was the rate at which the radius was changing was negative 1 over 40 pi. All right, so let's go ahead and try and simplify this a little bit. Remember, this 4 pi and the 25 is all like over 1. And so anything in the top can cancel with anything in the bottom. So I can cancel those pi's. I know I can cancel 4 into 40 10 times. All right, so what we end up with here is dv dt is equal to negative 25 over 10, which is the same as, of course, negative 5 over 2. All right, and now let's put a unit of measure. So if the radius was changing at centimeters per minute and the surface area was centimeters squared per minute, volume is going to be centimeters cubed per minute. Okay, so that is my dv dt. And again, in understanding of it, interpreting my solution, the volume is decreasing. It's melting, so it's decreasing at a rate of 5/2 centimeters cubed per minute. All right, good job, guys. Let's go ahead and move on to the next one. All right, number 4, a spherical shaped balloon. So again, we're talking about a sphere, okay, spherical shaped, is being filled at a rate of 100 cubic inches per minute. So make sure you catch that, 100 cubic inches. So when you are given they're not telling you directly what that means, but if we're talking about filling something and then the rate is in cubic inches, we know that that's talking about the rate of the volume. At what rate is the surface area of the balloon increasing when the radius is 12 inches. All right, so we're talking about a spherical, shaped balloon. And it's being filled at a rate. So we already talked about that. That means that's dV dt. And that's 100 cubic inches, so inches cubed per minute. At what rate is the surface area? So they want ds dt. That's what's unknown to us. Increasing when the radius is 12. So they give us the radius to be 12. All right, so let's go ahead and start with what is it that they have given us, okay? By this point, you kind of recognize that they're giving you one. Sometimes you have to use that to extract some information to fill in for the other one. Okay, so let's go ahead and start with our volume formula. Volume of a sphere is 4/3 pi r cubed. I go and take the derivative of that with respect to time, and I get dV dt is equal to 4 pi r squared dr dt. Okay, so I'm going to fill in my dV dt as 100. I'm going to go ahead and fill in my radius as 12. So 4 pi, 12 squared would be 144. And then dr dt. And in fact, that's what I'm looking for, okay? dr dt is my unknown, and I'm going to need dr dt to find the rate at which the surface area is increasing. All right, so let's go ahead and simplify this. Well, one thing I know I can do is divide by 4 right away. So I'm going to get rid of that and make this 25 equals 144 pi dr dt. Okay, so now I can divide by 144 pi, and so I get 25 over 144 pi equals dr dt. Okay, so that was the first piece of missing information that I needed. All right, so now I'm going to use that where? Well, I need the whole thing I'm doing is looking for the rate at which the surface area is increasing. So it sounds like I now need the formula for surface area, which, if you remember, surface area is 4 pi r squared. So take the derivative of that with respect to time, kind of running into each other here. Okay, so it would be ds dt equals 8 pi r dr dt. Okay, so ds dt is what's unknown to me, so I can't fill that in. 8 pi, my radius is 12, and my dr dt is 25 over 144 pi. Okay, remember this is all over 1. All right, so what can I simplify away? Well, I know that my pi's are going to cancel. Okay, I know 12 goes into 144 12 times. And then I can even further simplify this by dividing 8 and 12. So I know if I divide 8 and 12 both by 4, that would be a 2 here and a 3 here. So I'm just trying to simplify it so I have smaller numbers to work with. Okay, so after I do all that, I have ds dt is equal to, what's left in the numerator would be 2 times 25, so 50. And the only thing left in the denominator is 3. So 50 thirds, and now we need a unit of measure. We're talking about area, so it's inches squared per minute. Okay, and again, I would go ahead and write a concluding sentence. I'm going to save time and not, but I encourage you to take the time in your notebook and do it. The rate at which the surface area is increasing is 50 thirds square inches per minute. All right, number 5. Mrs. Calculus Rocks has a headache from her too loud calculus class. She goes to the math office to take some aspirin. The water cooler is cylindrical in shape with a radius of 10 inches and a height of 22 inches. She notices that the height of the water in the tank is 8 inches and is dropping at a rate of 2 inches per minute. How fast is the water flowing out of the tank? Okay, so let's unpack what we have here. Clearly we have a new shape. We have a cylinder. Okay, so let's remind ourselves what a cylinder is. Cylinder is like a soup can, right? So it's got a circle for the base, for your two bases. And the two critical pieces of information of units of measure for the cylinder would be your radius and would be your height. Okay? Okay, so we can write in that information that they gave us, that the radius was 10 and the height of this is 22. All right, now let's see what's happening in this. She notices that the height of the water in the tank is at 8 inches. Okay, so currently the water, even though the height of the tank is 22 inches, the height of the water in the tank at the time when she happens to go and take a drink from it is at 8. So this much is just 8 inches. All right, but it's dropping at a rate of 2 inches per minute. So the height is decreasing negative at a rate of 2 inches per minute. Okay, so the height of the water in the tank is decreasing at 2 inches per minute. How fast is the water flowing out of the tank? So if we're talking about water and it's flowing, okay, that sounds to me like volume. How fast sounds like the rate of the volume. So what am I looking for? dV dt is my unknown. All right, now, what I want you to understand with this problem, you always want to think this through. We haven't had any like this in today's lesson, but here's one. All right, think about a water cooler. The height of the water is going down, but is the radius of that water cooler changing at all? Okay, no. Your water cooler stays constant as far as the size of the base of the circle on the top and the bottom. The only thing that's changing is the height of the water inside the cooler. And so when I go ahead and start my formula with volume, that is going to be important to understand that my radius here is constant. Okay, and just like when we had the right triangle problems, we want to mark that down so we know that. All right, so let's go ahead and grab the formula for volume of a cylinder. So this is a new formula. Again, you're going back to your geometry days and remembering these formulas. So the formula for any cylinder, any prism, would be the area of the base times the height of the object. So the base here is a circle, so the area of a circle is pi r squared times the height of the object. All right? Now, remember, if you have a constant, you're going to go ahead and put that value in before you take the derivative with respect to time. So we're going to go ahead and plug in what we know to be constant, which is our radius. So pi times 10 squared times the height. So if we simplify this, we get volume is 100 pi h. Okay? Now we're going to go ahead and take the derivative of this with respect to time. So now we do the derivative with respect to time. So we get dV dt equals 100 pi dH dt. All right, and so we can go ahead and plug in what we know. The only thing we need is the dH dt. And we know dH dt is right over here. So dV dt equals 100 times pi times negative 2. So our answer here is that the volume is flowing out at a rate of negative 200 pi, and it's volume, so keep that in mind. That means our label has to be inches cubed per minute. So the volume is flowing out of the tank at a rate of 200 pi cubic inches per minute would be my concluding statement. Okay, last problem. Here we go. Number 6. Oil is leaking from a pipeline on the surface of a lake and forms an oil slick whose volume increases at a constant rate of 200 cubic inches per minute. Definitely important. Okay, and cubic indicates volume. The oil slick takes the form of a right circular cylinder. Okay, so we know we're dealing with a cylinder. all right, with both its radius and height changing with time. So this is different than the last problem we just did. It says both its radius and height change with time. So this time, both the radius and the height are changing, not just the height like the last one we did. At the instant when the radius of the oil slick is 50 centimeters and the height is 0.2. So my radius is 50 and my height is 0.2. So clearly we have a very wide, thin cylinder. The radius is increasing at a rate of 2.5 centimeters per minute. So dr dt is 2.5 centimeters per minute. And at this instant, what is the rate of change of the height? So what they're looking for is dh dt. And go back in the problem, what else did they give us? If you look at the very beginning, they gave you the dv dt. And it was increasing, so it's positive 200 centimeters cubed per minute. Okay, so looking at everything that they have given us, we're only seems to be talking about volume here. Okay, so we're going to write down the formula for volume of a cylinder, which is pi r squared times h. Okay, because of that sentence that I highlighted, that both the radius and height are changing with time, I can't replace anything because I have no constants. All right, so at this point I need to go right ahead and take the derivative with respect to time. All right, now when I do that, I notice dv dt equals, all right, pi is a constant, and then r squared times h is a product, so I'm going to have to use the product rule. So we've done this before. I'm going to pull out my constant and then do the derivative of r squared h, again with by using the product rule. So first times the derivative of h would be dh dt, plus second would be your h, times the derivative of r squared would be 2r dr dt. Okay, so dv dt is what I know, it's 200. Okay, pi times. All right, what do I know here? I know my radius is 50, so 50 squared is going to be 2500. dh dt is what I'm solving for, so I leave that unknown. Plus, my height is 0.2 times 2 times the radius is 50. Okay, and then dr dt is 2.5. All right, so 200 is equal to, all right, I'm going to go ahead and distribute this pi through. So 2500 pi dh dt plus, all right, let's see if I can do some of this in my head, right? 2 times 50 here would be 100. 0.2 of 100, well, I just moved my decimal place over 2 places, and that's 20. And 20 times 2.5 is 50. So this is really just 50, and then multiplying the pi through pi. All right, so I'm solving for dh dt. First thing I need to do is subtract away that 50 pi. So 200 minus 50 pi equals 2500 pi dh dt. Last step is to go ahead and divide by 2500 pi. So 200 minus 50 pi over 2500 pi equals dh dt. Okay, so it's a pretty ugly answer. And actually, I could do one thing. I could go ahead and divide everything by 50. And so I would get 4 minus pi over 50 pi. So it's a little bit better, but it's still pretty ugly. I cannot simplify that any further. All right, and so that is my dh dt, but of course I need a unit of measure. And so dh is height. I'm not talking about area or volume, so it just gets centimeters per minute equals dh dt. Okay, and a concluding statement would be that the rate at which the height of the oil slick is growing is 4 minus pi divided by 50 pi centimeters per minute. All right, guys, I know this was a lot tonight. Go back and make sure that you are seeing all the different kinds. Okay, so we did 2 on circles, 2 on spheres, and 2 on cylinders. And most important, please make sure you come into class next time knowing the formulas for area of a circle, circumference of a circle, surface area of a sphere, volume of a sphere, and volume of a cylinder. So you might want to take a second right now and just quiz yourself on those. Make sure that you know them for next time. All right, have a great night.